Today, we're diving into a critical aspect of product development that often determines the success of a project: the design and architecture phase. Research shows that 60% of a product's cost is committed during the concept and architecture phase. This phase has the most profound impact on the product's quality, reliability, serviceability, flexibility, and customizability. It's a foundation upon which the entire lifecycle of a product is built. If you want to shorten the time to market for your product, you can achieve this by almost 50% through comprehensive upfront work. For example, dedicating a third of your design phase timeline to optimizing architecture rather than rushing through it can yield substantial benefits. Before starting the design process, you must thoroughly understand the customer's needs, design specifications, and resource allocations. A crucial tool here is the requirements document. This document serves as the product's definition, outlining what the customer wants without limiting the flexibility or creativity of the architecture. By maintaining flexibility, you can explore multiple iterations, alternatives for components, and different functionalities to ensure the best alignment with the requirements. Ultimately, you aim to strike a balance where cost, time, and functionality converge into a cohesive product. Organizing your design process can involve creating a database or schema for your files, similar to the way programmers use version control systems like GitHub. For smaller projects, this might not be necessary, but it's a valuable tool for managing large-scale or portfolio projects. You can create a database to catalog your lessons learned, project summaries, and resources. For job seekers, this can even serve as an interactive part of your portfolio, showcasing your organizational skills and technical expertise. For those looking to impress employers, you could design an interface for the database, allowing hiring managers to query specific aspects of your portfolio. While this level of sophistication isn't required, it demonstrates a commitment to excellence that could set you apart. Whether you're working solo or within a team, you should ask key questions to guide your process. 1. Is the project timeline realistic given the budget? 2. Will resources be allocated on time and in sufficient quantity? 3. Are there red flags, such as an unstable product definition? Avoid throwing the design over the wall, a term used to describe situations where designers work in isolation, hand over their designs to manufacturers, and fail to collaborate. Effective communication between designers, engineers, and manufacturers ensures a seamless transition from design to production. In the field of design and engineering, specialization is critical. No one can memorize every equation, law, or principle, which is why experience and continuous learning are so valuable. Engineers often rely on notes, references, and specialized knowledge. For example, when creating custom or mass-produced products, the level of research required varies significantly. Custom products demand an intimate understanding of the customer's needs, whereas mass production focuses on efficiency and scalability. Design teams must focus on bottom-line metrics such as total cost and time to market. Beware of cutting corners by specifying cheap, low-quality parts, opting for vendors that don't support collaborative design, overemphasizing labor costs in sourcing and location decisions. Instead, prioritize optimizing the product architecture to create a design that meets customer needs while staying within budget and on schedule. In today's competitive environment, being multidisciplinary is key. Whether you're working toward a degree or teaching yourself through online resources, focus on creating a portfolio that showcases your ability to adapt and innovate. Download textbooks and resources to teach yourself new skills. Learn software tools like AutoCAD, SolidWorks, and Revit. Tackle small projects to build experience and demonstrate your capabilities. An entrepreneurial spirit can often take you further than a traditional academic path, especially with the rising costs of education. To wrap up, the design and architecture phase is where success begins. By committing time and effort up front, understanding customer needs, organizing your resources, and fostering collaboration, you can create products that exceed expectations while staying on budget and schedule. Now we will discuss the critical lessons learned in product development, focusing on risk mitigation, practical engineering approaches, and how to align academic knowledge with industry realities. This session is designed to illuminate key aspects such as 1. Risks that could have been mitigated early and how to do so effectively. 2. Risks that were not mitigated and their consequences. 3. Leveraging modern tools and methodologies to bridge the gap between design concepts and production realities. Risk mitigation starts at the concept stage of any project. It is essential to ask: what risks could have been mitigated early? How can those risks be addressed now? Before creating a fully developed product, start with a prototype. My approach, for example, utilizes a hybrid system combining Python and Fusion 360. This strategy allows us to achieve results comparable to more expensive tools like SolidWorks without the astronomical costs. Python enables advanced customizations like parametric studies, generative design, and multivariable optimizations. Fusion 360 offers a user-friendly interface for CAD modeling, simulation, and manufacturability analysis. By merging these tools, we can test and refine designs both visually and physically. This process is not only cost-effective but also leverages our skills to save money, reduce risks, and ensure precision. A critical aspect of design is the creation of parameters based on a detailed requirements document informed by customer input, research, and team expertise. While it may seem counterintuitive, constraints actually foster creativity. Without parameters, designs can become unfocused, akin to a symphony with too many clashing instruments. These parameters guide creativity toward meeting the project's goals. For example, if a specific material is unsuitable, explore alternatives. If a component is unavailable, consider designing one. Using Python for parametric modeling is invaluable here. Libraries like NumPy, SciPy, and Matplotlib provide tools for mathematical optimization and data visualization, making it possible to generate and refine parametric models efficiently. Moving from concept to production involves numerous external dependencies, such as partner suppliers and outsourcing, regulations and compliance, supply chain risks, like vendor reliability. Practical steps. Engage vendors early, especially for custom parts. Assess resource availability to ensure a complete team. Consider concurrent engineering practices to align design and manufacturing timelines. For small-scale or specialized projects, leveraging local workshops or hiring freelancers can be a cost-effective approach. For example, in my city, fabrication workshops provide access to various machines and skilled labor. Collaboration with welders or machinists can refine designs before production, saving both time and money. One key takeaway from my experiences is the gap between academic learning and industry practices. For instance, during a job interview, I toured a fabrication shop and realized how much more there was to learn about practical application and industry standards. Lessons learned. Interviews are invaluable for identifying knowledge gaps and gaining insights into real-world processes. Understanding the disconnect between theoretical concepts and practical applications is crucial for career growth. Success requires continuous learning, adaptability, and creativity. We live in a time where skills and creativity are paramount. This era rewards those who are willing to learn, adapt, and innovate. While traditional hierarchies and systems may present challenges, the gig economy and access to affordable tools like Python and Fusion 360 have opened new doors for creators and engineers. To summarize, early risk mitigation and parameter-based creativity are foundational to success. Hybrid approaches combining software tools like Python and Fusion 360 can optimize designs cost-effectively. Bridging the gap between theoretical knowledge and practical application is critical for professional growth. When approaching product design, it's crucial to avoid locking into a specific architecture or system design too early in the process. Keeping the design phase open as long as possible enables better optimization and allows for exploring various configurations and approaches. This mindset applies all the way to the fabrication level, where considerations like material usage, cost efficiency, and vibration resistance come into play. For instance, when choosing materials, you need to assess how much material can be used and whether the costs can be offset. In some cases, like when dealing with vibration-heavy environments, strong materials such as steel may be non-negotiable. These choices are informed by mathematical modeling and physics principles, such as load-bearing capabilities and vibration dynamics, often supported by tools like Python for simulations. This results in a holistic approach, addressing every requirement: functionality, reliability, maintainability, cost, and user experience, before manufacturing even begins. By creating multiple designs that meet the same requirements but differ in structure, materials, or functionality, you can compare options and identify the design that best balances factors like cost, performance, manufacturability, and customer satisfaction. This flexibility allows you to tweak and optimize elements of each design, leading to a more efficient and effective final product. Avoiding premature commitment to a single design ensures the decision-making process remains data-driven and objective, reducing risks of encountering manufacturability or customer satisfaction issues later. For example, if a customer's budget constraints require adjustments, you might substitute custom components with off-the-shelf alternatives. This might necessitate redesigning certain elements, fundamentally altering the product's appearance or functionality. While these changes may be necessary to meet cost demands, they must still adhere to industry standards and practical manufacturing requirements. This often involves close communication with manufacturers to ensure feasibility, such as confirming welders can fabricate the redesigned product. Sometimes, customers may have unrealistic expectations about what is feasible within their budget. They might seek alternative engineering firms when their demands can't be met. Designers must navigate these scenarios while balancing the trade-offs inherent in different designs. One design might be less expensive but less reliable, while another could be robust but costly. Keeping options open and analyzing these trade-offs systematically ensures the best overall decisions are made, optimizing the product for its intended use and customer satisfaction. By generating and analyzing various designs, you can identify the one that optimally satisfies requirements and constraints. This iterative and flexible approach is essential for creating high-quality, manufacturable, and customer-aligned products. Feasibility studies and methods like design of experiments, DOE, play a critical role in this process. Design of experiments, DOE. DOE is a structured methodology for conducting experiments that assess how different variables affect outcomes. This approach ensures statistical significance, making results reliable and not merely coincidental. Python, for example, is often employed in this context for mathematical modeling, facilitating robust experimentation. Key stages in product testing include: 1. Prototype testing, developing and testing early product versions to iteratively refine designs. 2. First article and beta tests, evaluating initial production samples or beta versions under real-world conditions. 3. Pilot production testing, ensuring consistency in manufacturing processes and product performance. Tolerances. During design, it's crucial to account for acceptable variability in product dimensions or performance. For instance, welders may require a specific gap, e.g., half an inch, to perform their work, which must be factored into the overall design. Consulting expertise. Organizations like PCA.org or Guideline.com provide access to consultants and technical experts who can offer insights into complex engineering challenges. While consulting can be expensive, it might be critical for assessing feasibility when internal knowledge is insufficient. Balancing learning and expertise. Deciding whether to acquire expertise internally or consult external experts involves weighing the trade-offs between time, cost, and practical experience. Relying solely on theoretical knowledge or modeling software can sometimes fall short compared to hands-on experience. Challenges in product development. The biggest roadblocks in creating a product often stem from poor communication, lack of questions, and insufficient testing. It's better to voice concerns early, even if you're wrong, than to face costly mistakes later. Simulation and risk management. Using software tools to simulate product performance, e.g., stress, thermal, or motion analysis, and manufacturing processes helps identify and address potential issues early. Proactively identifying risks, like technical failures, cost overruns, or production bottlenecks, is crucial. In some cases, manufacturers knowingly produce flawed components, offering to fix them for an additional cost. This practice is unethical but highlights the importance of thorough risk mitigation strategies. Failure modes and effects analyses, FMEA. FMEA is a systematic method for identifying, analyzing, and prioritizing potential failures in a product or process. Key steps include: 1. Identify potential failures. Determine how components, subsystems, or processes might fail, e.g., material fatigue, software crashes. 2. Analyze effects. Assess the consequences of failures on the system or user. 3. Determine causes. Identify root causes, whether design flaws, manufacturing defects, or improper usage. 4. Rate severity, likelihood, and detection. Assign scores, 1 to 10, for how severe, likely, and detectable failures are. FMEA also draws parallels with fields like medication trials, where risks and probabilities are meticulously calculated. For example, regular maintenance schedules, such as changing a car's oil every 6,000 miles, help mitigate failure risks. Entrepreneurial approaches can integrate software with products to predict and diagnose failures. For instance, modern cars notify drivers about potential issues or upcoming maintenance needs, preventing larger problems. By systematically identifying components, brainstorming potential failures, and evaluating risks, FMEA enhances reliability and minimizes costly errors. This process underscores the importance of proactive design, robust testing, and clear communication to deliver successful products. Detectability in a system, whether it can be addressed through software or requires physical intervention, is a crucial question. To resolve issues effectively, we need to ask whether problems can be detected and corrected via programming or whether a manual disassembly and adjustment of the machine is necessary. Ideally, we aim to design systems that reduce the likelihood and severity of failures while increasing detectability. This iterative design process involves multiple prototypes. It's not as simple as designing one version and finalizing it. Typically, 6 or more drafts are developed for a single product. These drafts are evaluated in meetings to determine which one aligns best with the requirements document, ensuring the product meets its intended specifications. This thorough approach explains why the process takes more time than expected. One way to quantify and address potential risks is by calculating the risk priority number, RPN, which is the product of severity, likelihood, and detectability. High-risk items identified through this process can be mitigated by redesigning components, adding redundancies, or enhancing quality control measures. Following improvements, it's essential to reassess and update the failure modes and effects analysis, FMEA, to ensure the system performs as expected. Programming, particularly with Python, can significantly automate aspects of the FMEA process. For example, Python can be used to calculate the RPN or run simulations to identify likely failure modes. Custom code can generate warnings or create automated FMEA charts based on specific scenarios. This eliminates repetitive manual work, allowing engineers to focus on critical decision-making. Tools like Fusion 360 complement these efforts by offering simulations, such as stress tests and thermal analysis, to model and predict potential failure points. Python can also run probabilistic analyses, simulating thousands of iterations to identify potential failure scenarios. This process can be further enhanced with machine learning and advanced statistical methods, such as Bayesian equations or Gaussian processes, to make data-driven decisions. Libraries in Python support these approaches, enabling the automation of complex analyses. The overarching goal is to mitigate risks while optimizing resources. Iterative simulations, refinements, and automated processes not only save costs but also reduce stress and allow engineers to focus on what truly matters. By leveraging programming, simulation tools, and AI, companies can elevate the FMEA process, minimize risks, and streamline product development, all at a relatively low cost, apart from the time, patience, and mental energy invested. To carry out complex engineering tasks, a robust computer system is essential. This includes having sufficient RAM and a powerful CPU to handle the demands of the simulations and designs involved. Software like Fusion 360 can be used to visualize design scenarios, validate them through computer-aided engineering (CAE) simulations, and refine those designs to mitigate potential risks. CAE simulations are a fundamental tool in modern engineering. These simulations break down a 3D model of a product into smaller elements, then apply forces, boundary conditions, and other variables to analyze how the product behaves under different conditions. This approach uses a stiffness matrix to calculate the resulting responses, helping engineers to predict how the design will perform. When working with CAE, the product design is divided into smaller elements such as pyramids, tetrahedra, blocks, and wedges. Each of these elements has nodes, or corners, that are used to create a stiffness matrix, which forms the core of the simulation. The stiffness matrix is integral to the finite element method, FEM, which is used to solve elliptical partial differential equations that describe the behavior of materials under various loads and conditions. The material properties, such as density, Young's modulus, Poisson's ratio, thermal conductivity, and specific heat, are crucial for CAE simulations, as they determine how a material will react to stress, heat, or other forces. Additionally, constraints, such as structural constraints that prevent motion or thermal constraints like fixed temperatures, must be applied to model real-world conditions. Loads are another important factor in simulations. These include structural loads like forces, moments, pressure, and gravity, as well as thermal loads such as heat flow. By defining these loads, engineers can simulate the conditions the product will face in the real world, such as operating temperatures or environmental forces. Once the mesh, material properties, constraints, and loads are set, the simulation can be run. The results from the simulation can then be analyzed both numerically and graphically to assess factors like safety margins and performance. This analysis helps determine whether the product will withstand real-world conditions or if it needs redesigning. In terms of specific analyses, CAE includes modal analysis, which examines the natural frequencies and vibration modes of a product to avoid issues like resonance. Thermal analysis calculates heat flux and temperature changes under conditions like conduction, convection, and radiation, while fluid analysis evaluates how liquids and gases move through and around the product. Together, these analyses provide a comprehensive understanding of the product's performance under various conditions. Ultimately, CAE tools are essential for ensuring that designs are not only functional but also safe and efficient. They allow engineers to predict potential problems and make necessary adjustments before manufacturing, saving both time and resources. To create our own library for simulations, the most critical requirement is an interface that allows mathematical models to be expressed, essentially through simulation. This simulation is primarily based on graphics, and while Python is commonly used for this purpose, it can be combined with Rust. Although Rust isn't widely popular yet, it has advantages in handling graphics, especially in video game development, and could be a useful language for our needs. Rust could help us minimize costs while achieving the desired functionality. CAE, computer-aided engineering, simulations provide a significant advantage to product development teams by enabling faster market entry and lower costs. These simulations help reduce iterations during the design process, generate prototypes with first-time quality, and ensure these prototypes are validated under their operating conditions. This leads to narrowing down test programs to only the necessary runs, reducing development time, and cutting down manufacturing tooling, material, and resource costs. The result is more reliable products that satisfy customers while also lowering service and warranty costs for manufacturers, improving both schedules and budgets. While Python alone does not specialize in engineering simulations like stress, thermal, or motion analysis, it can be extended to perform these functions through various libraries. For numerical analysis and visualization, Python libraries such as NumPy, SciPy, and Matplotlib are useful but relatively generic. To tackle more complex simulations, specialized libraries like SciMPy for simulations, PyBullet for motion physics, or open foam bindings for fluid dynamics can expand Python's capabilities. Python can also be integrated with external software tools such as Fusion 360, Blender, or ANSYS through their APIs, allowing it to run advanced simulations. By using Python, we can generate parametric models, automate repetitive tasks, and handle the pre- and post-processing of simulations conducted in these tools. For more advanced simulations, we would likely need to develop a custom Python library tailored to handle the specific calculations required, interfacing with other software for more realistic rendering and simulation outputs. In engineering, risk is often evaluated using the risk priority number, RPN, which considers the severity, likelihood, and detectability of potential failures. The formula for RPN is severity, S, times likelihood, L, times detectability, D. A higher RPN score indicates a need for immediate action to mitigate risk. To reduce risk, engineers might redesign products, add redundancies such as backup systems or fail-safe mechanisms, like dual braking systems in vehicles or additional support beams in construction, and enhance testing and inspection protocols. For high-risk items, redundancies are crucial, even though redundancy is typically avoided in programming due to inefficiency. Furthermore, machine learning, ML, can elevate the process of failure modes and effects analysis, FMEA. ML can analyze historical data, identify patterns, and predict failure modes under similar conditions. By dynamically calculating and prioritizing RPN values, ML models can identify critical risks in real time. These machine learning models can be integrated with simulations to process data from them and generate RPN values. This integration would also link to a database schema where we can store past project data, create reports, and automate the documentation process using tools like SQL. This would enable us to systematically manage and analyze the simulation results and the associated risks in a more efficient and organized manner. When presenting your portfolio or product, it's crucial to document every aspect of your process to ensure clarity for anyone reviewing your work. This includes details about the tools and techniques you used, such as programming, machine learning, and simulation software. If you're aiming to secure a job or get into college, comprehensive documentation is essential. While some proprietary information may remain confidential, the broader steps you took in creating your product should be shared. This will allow others to understand exactly how you arrived at your final product. A key part of this process is organization. Whether you're using databases, programming languages like Python, or machine learning algorithms, everything must be carefully structured. Tools like SQL can help you maintain an organized database that tracks every step of your work. I've shared some introductory videos on my channel about databases and SQL, which, while basic, provide a foundation that I can expand on as needed. Organizing your work allows for clarity and efficiency, especially when working with machine learning systems or running simulations. For example, machine learning-driven systems can monitor various factors such as vibrations and temperature changes, taking preventative actions in real time. This dynamic, collaborative process involves coding and data collection, which must all be organized within appropriate environments. Multiple environments may be necessary, and connecting them efficiently can help conserve hardware resources. It's important to streamline CPU and hardware usage while ensuring all elements of your project are interconnected. Without organization, chaos can ensue. Whether you're working with software, programming code, machine learning models, simulation tools, or the data itself, every component must be carefully documented and structured. One of the most valuable aspects of building a portfolio is that it's not just aimed at landing a single job. It's designed to showcase your versatility and can be tailored to various fields, whether it's CAD design, machine learning, data engineering, or software development. The first project is often the most challenging, but once completed, it serves as a springboard to future growth. From there, you can continue to expand and refine your skills, building on each project as you progress. As the saying goes, the more you know, the more you realize you don't know. This process of continuous learning, often referred to as the learning curve, fuels your growth. With each project, you gain more knowledge and experience, propelling yourself further. Once you create that first project or land your first job, you're on an unstoppable path. It's the pivotal moment in your career. Getting that first project or entry-level position is a significant milestone. For many, the challenge is figuring out what they want to do with their life. But once that decision is made, the possibilities are limitless. Unlike those who are content with sticking to the status quo, the entrepreneurial spirit of my generation drives us to continually learn and expand. The traditional 9-to-5 job doesn't appeal to everyone, and many are looking to create their own opportunities. In the context of machine learning, frameworks are essential. For instance, if you're working with historical failure data, you can input this data into machine learning models to train them. This allows your simulations to become more accurate and responsive, drawing from real-world data to improve the system's performance over time. The outputs of these simulations further refine the model, creating a cycle of continuous improvement.